All right, round two. I made sure to put the screen share on this time. Let's record the lecture videos for section 4.2. This is on linear approximations and differentials. Think about the way we did found the slope even with the regular line before derivatives in calculus. We had rise over run, which was y2 minus y1 over x2 minus x1. That equaled m. And if we cleared fractions, we could multiply both sides by x2 minus x1. And then we get y2 minus y1 equals m times x2 minus x1. What we're going to do is we're going to drop this 2 subscript right now. We're going to get rid of that. And we're going to add y1 to the other side. And when we do that, we get y equals y1 plus m times x minus x1. And if we look at y equals f of x, and we look at what's going on when x1 equals a, we get y1 is like f of a, and m is going to be f prime of a. That's we could find the derivative there, bring some calculus into it. And we get f of x equals f of a plus f prime of a times x minus a, just making these substitutions in here. And we're going to call that L of x. L of x stands for linear approximation. This is a form of the equation for the tangent line at a for some curve f of x at x equals a. Okay? We take a look at what's going on. F of x can be all crazy looking, like this line right here, just crazy. But let's say x is a right here. I'm going to zoom in. My orange line is my tangent line. And if I go out like a distance delta x is like a dx. If I go out a distance delta x, delta y would be the change in y. Like y rise over run is delta y over delta x. That's another way they write it. And so delta y is just doing this little piece right here. Now, if we did it like a dy using the line, we're going to call this distance from here to here. Let's change color so it shows up. Pick a color that's not there. This distance from there to there is going to be dy. Okay? And you'll see where that comes from in a second. Notice delta y does not exactly equal dy, but they are pretty close in length, especially when I zoom back out, and we can see that it's not that much different. In fact, the closer or smaller delta x gets, let's say it was right here, then the actual distance between them, it gets even smaller. It's just that little tiny piece. So this is kind of how we're going to use it. And so L of x is going to approximately be f of x, because f of x is the white line, and L of x is our orange line. So like near this point x equals a, near here, they're approximately going to have the same value. And that's why we call it a linear approximation. Approximation because it's approximately the same near it, and linear because of line. And finding values or getting values on a line, the calculations are much easier to do. You can do them by hand. Whereas if you're doing stuff with like crazy curves, the math can get horrendous. So that's what we're looking at here with what we're doing. I don't know why I zoomed so far out. So we can use these to estimate values. We know what the square root of 16 is. The square root of 16 is 4. But what do we know about the square root of 14? Well, we're going to come up here. We're going to use this equation right here. Let's use that. And so I have that written here in blue. We need f of x and we need f prime of x, and we need to evaluate it at a. A is going to be the value we know. Value you know. Oh, wow. That sounds like you know the card game. All right. So what kind of function will we use? The square root of 16 makes me think square root of x. So we're going to use square root of x for the function, and that's x to the 1/2 power. If we take the derivative, we have 1/2 x to the negative 1/2. I rewrote that by moving the x to the bottom because it's got a negative exponent and putting back in the square root. If we plug in 16 for a, because we need f prime of a, and a was 16, we get 2 times the square root of 16 on bottom, which is 2 times 4, which is 8. F prime of a is going to be 1/8. Okay? We also needed f of a. That's our first thing right there. We need that as well. And f of a just comes from plugging in 16. And we get, that's our f of a right there. F of a equals 4. So we've got everything we need. This is a 4. This is the 1/8. And a was 16. We have our linear approximation is 4 plus when we stick in the 1/8. Let's do that now. We got 4 plus 1/8 times x minus 16. We could actually change that, clean that up some. Let me redo this. There we go. I could distribute, and I've got 4 plus 1/8 x minus 2, which means we've got 1/8 x plus 2. And you'll see if we plug in 17, because we were looking for that value, we wanted square root of 17, that's going to be our x. So we're doing the linear approximation at 17. Okay? So we plug in the 17, we got 4 plus 1/8 times 1 here, which is going to give us 4.125. Okay? Be the same thing if we had plugged in the 17 right here. Going to end up being the same value. It's just written in a different form. So we got 4.125. The actual value of the square root of 17 is 4.123. We are literally off only in the thousandths place. Tens, hundreds, thousandths. And it's not even by a lot. A whole 0.002 off. That's pretty close. And 17 is like a full number away from 16. So 17 is not that close. If we go even closer, like if we looked at 16.2, if we wanted to do the square root of 16.2, we could use the same formula, same setup. We're going to do L of 16.2. We plug that in. We're going to get 4 plus 0.125 times that 0.2. I did that by hand over here because I wanted to show that you don't need a calculator to do it. And ended up getting 4.0250. I got a linear approximation for the square root of 16.2. And if you actually plug in 16.2, the square root of it in the calculator, you get 4.0249 and some change. These are to the, like, it's close to the 10,000th place. That's pretty close. And yet, I couldn't do square root of 16.2 by hand. I can do the linear approximation by hand, and it was only require a little bit of multiplication and addition. So that's where this is good for. You have to set up the equation that we have right here. f of x equals f of a plus f prime of a times x minus a. It really comes from, just wanted to show you, it comes from our rise over run formula. Or in this form, this is called the point slope form. And I move the y1 over. These both are like the point slope form. But we just changed it. Instead of using y1, x1, and y, we put in f of x. Same thing. So why don't we try this with the cube root of x and do x equals 8. And then we can approximate the cube root of 8.1. I want you guys to try this doing what I did above. You got to find out what the cube root of 8 is. You got to take the derivative of f of x, plug in the 8 to get f prime of a. And then you got to set up that equation, and I'll just underline it real quick right here so you can see a little bit better. So we don't need to scroll up. That's the equation we're plugging in. Okay. I'll assume you took a look. If a equals 8, our exact value, if I plug in 8, the cube root of 8 is 2. So f of a is 2. If I take the derivative, I've got f prime of x is 1/3 x to the negative 2/3. And I rewrote that in the radical form with 3 times the cube root of x squared on bottom with 1 on top. Luna, go on. Go on. It's okay. And then, so we need that at 8. I need to do this at 8 right here. We need to calculate that at 8. So I did f prime of 8. I plugged it in. 8 squared is 64. The cube root of 64 is 4. 3 times 4 is 12. So that slope is 1 over 12. So I went and plugged in what we have. We have f of a being 2. We have f prime of a being 1/12. And a was 8 from over there. So 2 plus 1/12 times x minus 8. Plugging in 8.1, I got 2 plus 1/12. Just to show you, you can do this by hand. In fact, it might have even been easier if I distributed. We'll look at that in a second. 8.1 minus 8 is 0.1. If I did that over 12, I can move the decimal point, and it becomes 1 over 120. 1 over 120 isn't the easiest thing to do, but you can do division by hand. And I got 0.00833333. So I have 2 plus that 0.00833333. I went to 6 decimal places. You want to go one larger than what it says. It said 5, so I went 6. That way I knew whether I needed to round down or round up. This says I needed to round down, so I got approximately 2.00833. If you throw that in the calculator, the cube root of 8.1 is 2.00829,885. I don't know why I wrote actual retail value. I had like Prices Right or some shit in my head. Those are pretty close though. Look how close those are. And yeah, the division wasn't all that fun, but I can do it by hand. Okay. Let's try another one. We're going to do f of x is 1 plus x to the nth power. I guess that arrow doesn't need to be there yet. I should probably have that in white. And we're going to check that out at x equals 0. I'm going to use it to approximate 1.02 to the 4th power. So if I want to approximate 1.02, that's kind of like writing it as 1 plus 0.02. 0.02 is going to be my x right there. But for now, we need to do, I said our a. Our a is going to be 0, our value that we're starting with. That's going to be our a. So if I plug in a equals 0, I get f of 0, 1 plus 0 to the n is just 1 to the n, which is just 1. If I take the derivative, I bring the power down, lower the power by 1. And then I got to plug in x equals 0 there to get that. F prime is 0. Again, we've got n times 0 plus 1 to the n minus 1 power. 1 to any power is just 1. So f prime of 0 is just n. So I needed that, and I needed f of a, and I needed a. For my linear approximation, we have those pieces. We're going to plug them in. F of a was 1, f prime of a was n, and then a was 0. When we multiply that out, we get 1 plus n times x. And I just rearranged it so that the nx was in the front, right there. Okay? We do want, whenever we're using these approximations, x needs to be close to the a for the approximation to be good. And I'm going to go up to the graph and point out to you kind of like why. Let's go back up to that picture we had up here. I have x equals a right here. If I chose like a different x to work with my a over there, this is f of a, and this is up here is L of a. Not L of a, L of, say, x1. x2. And notice they're not anywhere, that's a big gap. So when you do your approximations, you want the distance you go from it to be relatively small. Okay? Whoa. Get rid of some of that writing. Come back down here and look at what we're doing. So we got nx plus 1, and we're going to use this to approximate the 1.024 to the 4th power, which means n equals 4 looking at it. That's got to be my n. And we have everything else. So we're going to approximate 1.02. That is like 1 plus 0.02 to the 4th power. We can see x equals 0.02, n is 4. We plug that in. We got the linear approximation is 0.02. 4 times 0.02 plus 1 ends up being 1.08. If you do the 1.02 to the 4th power in the calculator, you get 1.08243216. So it's pretty close. Okay. And that'll be it for the first video. Let me hit pause.